Hello there, children. Today, we are going to work on Section 4.4, Properties of Graphing Sine and Cosine. This educational experience is brought to you. You're a super cool guy of sine, cosine graphing. That'd be me. So today, we're going to look at graphing sine and cosine. Now, in order to graph sine and cosine, let us create a t-chart using some key values to help us graph. Now, why did I pick these particular values over here? Well, they all come from my unit circle. And if we recall, sine of x, f of x, or you will also see it as sine of theta, f of theta, because we're putting a theta into our function. Now, why did I pick this particular point? Because sine, remember, is our y value, and these coordinates, when put into sine, give us back some nice, pretty y values. Now, notice, I also am using the radian equivalent here. Using radians, you will have to graph in radians because it creates you a much nicer, tighter, prettier picture. So what is the y value at 0? Why, it's 0. What is the y value at pi over 2? Looking on a unit circle, that's 1. What's the y value at pi? 0. 3 pi over 2, that gets me a negative 1, it's 270 degrees. And 2 pi gets me back to 0 again. So what I'm going to do is I'm going to plot these particular points. Now, obviously I keep going on forever and ever and ever because I can keep going around and around my unit circle, but I'm only going to graph these particular values as of right now. So I'm going to graph these. Now, what I've got to realize here is that when I graph these, I'm going to graph and mark my x values. I have 0. I'm going to leave myself every couple just because I can. Pi over 2, pi, 3 pi over 2, and 2 pi. And then I'm going to plot these points. Now, at 0, what's my y value? That's 0. At pi over 2, right here, I get 1. I'm going to grab myself, put it up every 4 just because in this particular case, I want to show you exactly what the picture is doing. You can set your own scale, obviously. So I get 1 there. At pi, I get 0. At negative 1, I'm at 3 pi over 2. And here, now we connect our graph with a smooth curve. I don't want jagged like a heartbeat monitor. Nice, smooth. And now, for our purposes, what we're going to graph. But remember, this graph goes on like that forever and goes down like that. We'll talk about that later, but it's going to make this curve where it keeps going on forever and ever and ever. If you were to graph this on your calculator, that's what picture you would get. So this is the sine of theta, or x. That's the basic graph of it. Now, what does the graph of our cosine look like? Now, cosine here, we are going to introduce, again, picking our values over here. Now, you can pick whatever values you want, but remember, these are the ones I will always graph. I call them my big 5, or my 5 key pretty points, because for sine and cosine, they regularly give me nice particular values. So, remember, cosine is x, so at 0 degrees or 0 radians, my x value is 1. At pi over 2 or 90 degrees, my x value is 0. At pi, it's negative 1. At 3 pi over 2, it's 0. And back to 2 pi, it's 1 again. These are nice and pretty to graph. I don't want to have the situation where I try to graph, let's say, pi over 6, which would give me the value of root 3 over 2. Anyone know off the top of the head what the exact value is so I can plot that? Yeah, that's what I thought. I mean, it's a decimal, it's like 0.86, but that's not something I can easily plot. This happens to be something that I can plot regularly. So let's go ahead and plot that and see what the shape looks like. So again, let's give this a whirl. So I go ahead and I graph this wonderful thing. Now, I am going to plot my points. These are the points that I'm going to try to start out plotting at all times. Now, we'll talk about in class, they might move at some points, move around, so I'll have to find different ones, but these are what I call the big five, or the 5 key pretty points. And forget there's one at 0 there as well. Now, referring back to your notes in your T-chart there, what value do I get when I take 0 here? Well, that's going to get me 1. Boom. What value do I get at pi over 2? I'm going to get a 0. How about at pi? I'm going to get the x value of negative 1. At 3 pi over 2, I get 0. And at pi over 2, and there should be a 2 in front of that pi, it gets me to that point. So, plotting all of these things, you're going to get this smooth curve. Now notice I graphed this one in pieces because I'm graphing it on the board, and it's a little hard to do it once. You, on your paper, will be able to graph it a lot easier. And if it kept going, it would keep going like that, and down like that. And if you graph this in your calculator, you will see that it will keep going on in this particular pattern forever. I can go around and around my unit circle forever. So that's something we always have in our back pocket. Now, what we've got to cover now are the definitions, because these are not going to be the only way these trig functions are going to look. They are going to be able to move left, right, up or down, stretched out, shrunk down and compressed. So, flipped, we've got to talk about some transformations. So, in general, we have the following two items. Y equals A times the sine of the quantity bx plus c plus a d value, and the same thing in terms of cosine. So what that means, that's a star, by the way, that means for multiplication. So essentially, to pick on the sine version here, we have y equals A times the sine of a bx or a b theta plus a c value. That's not as complicated as it gets. What that means is you could have a coefficient out in front of your sine. You could have a little linear equation inside here. You could just have a coefficient. You could just add on something at the end if you wanted to, or you can have a little mini linear equation. And you can add values at the end for both sine and the cosine version. And for the interest of fairness, we will have the cosine version right here, just to show you what it looks like. Now, what we are going to show then is we are going to show you what exactly each of these transformations does. It'll be very note heavy, very definition heavy. So let's begin. The first one being amplitude. Amplitude. Definition of amplitude. The amplitude of a sinusoidal, which is what these graphs are called, function is half the distance between the max and the min values, i.e. half the wave. In terms of our function from previously, it's the absolute value of A. What does this mean? That means you take your A value, your coefficient, out in front of your function. The absolute value of that is your amplitude. And we will talk about that in terms of graphing in a little bit. All right, the next definition, periods. The definition of a period of a sinusoidal function is the distance between any two sets of repeating points of the graph of the function. For us, our period for sine and cosine is 2 pi divided by the absolute value of b. That means my absolute value of the coefficient of my x value. Remember, just picking sine because it's the easiest one to write out for me. Our b value, if we have this thing all laid out with every possible transformation we're going to come up with, right there. Now, a lot of times, that's 1. And if you think about it, for our original graphs we graphed sine and cosine, the period is 2 pi. And how long does it take me to get around the unit circle? 2 pi. Huh. Coincidence? I think not. And the last of the big transformation we're going to talk about today is a phase shift. The phase shift of a sinusoidal function is the difference between the horizontal positions of the function and that of an otherwise similar function. So how to find a phase shift? You take negative c over the absolute value of b again. So, looking at what our sine function looks like, what we're going to end up doing and the big thing here is the opposite of that. So if it's a plus pi, you're going to put the opposite there because it'll be the negative version of it. So it ended up being the opposite of that, and obviously the absolute value of b. So now we need to talk about what all of these things actually ends up doing to my graphs, because we have three things that seem very confusing. What do they all end up doing? So what do they mean for us? Amplitude. Amplitude we will call our stretch or our shrink. Why? Think about that for a second. It is the coefficient of my function. So if I had this again, remember, amplitude deals with my a value. I'm going to write sine again simply because I like writing the word sine. I don't know. You can write cosine in your notes if you like. It means the same thing in terms of the transformations. So that number right there, if you think about it, whatever value I put in, this number out in front there will simply multiply my y values by a certain value. So we will stretch it if it's above 1, or shrink it if it's a fraction, like 1/2. What does a period do? That's like our accordion. What does that mean? The period for us is how long my function is going to take to make one loop. In terms of sine, remember, this was a loop for us. Just a rough sketch here of what sine looked like. It was the graph in blue. It went from starting up, going to the top of the mountain, down to the valley, and back to the start again. So the period for us is how long it takes to make one cycle of my graph. So when we have different periods sometimes, this loop will get stretched out along this way, or it will shrink down. We will do tons of examples of this in class. A phase shift. A phase shift is simply a left or right move. That's a left or right shift. Meaning, if I move this value around, my function is going to slide out to the right or to the left. Now, what's great about our phase shift is our phase shift will follow the same rules as every other graphing thing we've done in class. Namely, remember, opposite on the inside. We'll talk about that in class. And the last shift we haven't really talked about yet is a vertical shift. That is simply D. That is our D value right at the end here. And whatever that is our up/down shift. Not to be confused with downshifting a car. But we are going to practice a ton with these in class. But just to give you, you need to know the terminology of when I say an amplitude, oh, that means my function is going to get stretched out like an accordion. Or period, it's going to take a lot longer to do one cycle or a lot shorter. Phase shift, it's going to move to the left or to the right, either direction. Vertical shift, it's going to go up or it's going to go down. But now that you have these particular definitions, we can talk about our function a little bit. You are prepared to do whatever homework I assign you? Go henceforth and do. Oh, happy days are here again.